So, if we were to arrange the periodic table in this fashion to be able to start looking at orbital notation, the periodic table isn't a perfect instrument, okay? It's sort of the best two-dimensional arrangement we can come up with, but there are some shortcomings that you kind of got to know about to figure out how to make it work the best for you. And one of the shortcomings when we're doing orbital notation, or electron configuration for that matter, is that helium's kind of poorly placed. Okay, now most of the time it kind of belongs there. That's the best place for it. It's a noble gas. It's on top of the column with all the other noble gases. It belongs there. But when we're talking about orbital notation, it's best if you can think about helium as belonging right here. Okay, that's why I have it circled and drawn to put it over here. Okay, so it best fits right here when we're talking about orbital notations and electron configurations. Okay. Something else that I want you to think about is that each one of these rows on the periodic table represents a primary energy level being added to an atom, or added to all atoms. Okay? So by the time we get down here to the very bottom row, we have 7 primary energy levels in all those atoms. Okay? So those concentric circles we talked about, or concentric spheres, are the primary energy levels, and where we're stacking those electrons on the outside of the atom, or outside the nucleus. All right? So once you've got this kind of in mind, then figuring out orbital notation starts to be a little bit easier. And we'll kind of leave it up here for a minute. And what we want to do is to have out your periodic table. And remember, hydrogen has 1 proton, therefore a hydrogen atom has 1 electron. So hydrogen is in the s sublevel region. So the new electron, in this case the only electron we're adding to hydrogen, is going to be an s sublevel electron, and the electron is going to be in the first primary energy level, okay, because it's in the first row. You with me so far? All right, so we're going to represent that as first primary energy level, s sublevel. Okay. Now, some of you I know in physical science probably did electron configurations, and this is somewhat like that. All right. But this is where the similarity starts to diverge from this point, okay? Because now we're going to use orbital notation to represent not just sublevels and the electrons within them, but we're also going to represent orbitals themselves. Now, we're not going to draw the shape of an orbital, okay? What we're going to do is just create a little place to put electrons. And for us, anyway, we're going to make it a box, okay? Just a simple box, all right? And that's our representation in this sort of inventory of electrons. That's our representation of an orbital. Remember that orbitals don't have a box shape. Okay, they have that double mushroom head shape if it's a p orbital, and a sphere if it's an s orbital, and even more complex shapes if it's a d or f orbitals. But don't worry about those, because in this class we don't worry about the shapes of d and f orbitals. Okay, we're only going to do s and p's. What?
What does 1s stand for?
The first primary energy level. So we're starting out in the first primary energy level, this first row of the periodic table. Okay, this first row. And we're in the s sublevel region, these first 2 columns. Okay, so the electrons that we're adding onto hydrogen are in this 1s primary level sublevel. Okay.
Tell me what you're adding to it?
Well, that'll make more sense as we get to the next atom. Okay. I use that term because if I just say, well, just bear with me a minute. Okay, it'll make more sense as we go along. All right. So now, what kind of charge does an electron have? A negative charge. Have you ever done the little thing in physical science with pith balls where you put them close to each other? No? Okay. Do you recall from physical science what happens when you put 2 particles together that have the same charge? They repel each other, like 2 north ends of a magnet. Okay? They push apart. All right? So we know that we can put up to 2 electrons in the same orbital. How do we keep them from flying apart? How is it they can do that? Well, what we call that is spin. And it's sort of related to another thing you'll learn if you ever take physics. You'll learn about it. When you have electricity flowing down a wire in this direction, okay, there's an electromagnetic field that's set up around that wire that runs in that direction, all the way around the wire. So if my thumb points the direction of the flow of electricity, the electromagnetic field goes this way. It spins around it. Okay? How many of you know what coaxial cable is? Okay, one or 2 people do. Okay, all right. Coaxial cable is what takes the signal from cable TV or from satellite to your house. Yeah. Yeah. Okay. All right. So what happens in coaxial cable is the signal first of all goes down the inside wire this way to your TV set or to your receiver device, and then back the outside. There's a set of braided wire around the outside that goes the other way, and the combination of those two cancels out the electromagnetic field to get rid of any interference. Okay. Well, in the same basic idea sort of applies here, where if the theory is that if the electron's spinning in one direction and the next electron is spinning in the other direction, they'll cancel out the electromagnetic fields and make them want to fly apart. But you can only spin two opposite directions, so you can only get two electrons in an orbital. Okay? Now, we could represent a spin like this, if we wanted to. Okay? That makes sense? Could we do that? That makes sense as a spin? And if I want to do an opposite spin, I guess I'd do something like that, right? Okay? And we could do that. Okay, we could do that. But that's a little bit complex. So rather than doing spins like that, let's do spins like this. Just enough arrow. I'm doing half an arrow because it makes it easier to write. It's faster because we're going to do a lot of these. Okay? I'm just going to make it an up spin. Okay? Well, there's only one electron in hydrogen. That's it. That's the orbital notation for hydrogen. Okay? A lot of explanation there because I'm setting up everything that follows. Okay? All right, so let's look where we put helium now. It's in the same S sublevel region. It's still in the first row. Okay? So if I'm going to do the orbital notation for helium, then that's going to be in one. It's going to have a 1s electron. It only has one orbital. And the other electron can have an opposite spin. Up, down. And that's the electron, or orbital notation rather, the orbital notation for helium.
Wait, the helium has an up and a down arrow?
Yep.
Because of the hydrogen?
Because I only have one orbital here, okay? And within that orbital, I need to put two electrons, and to get two electrons in the same region, they have to have opposite spins.
So why didn't you put another arrow for hydrogen?
Because hydrogen only has one electron.
So it's like if lithium is 3.
Exactly. Lithium will be 3. I'll get to that next.
Arrows?
Huh?
So whatever the number at the top, you point number,
Mm-hmm.
that's how many arrows it'll have?
That's how many arrows. It's exactly right.
So after you have, if you already know what the 1s and how many of those numbers and letters you're gonna have, the arrows are just counted.
Pretty much.
And we'll have a periodic table on our test.
Yes, you'll have a periodic table on your test. And it's not hard to figure out the regions from the periodic table, is it? No. Here's S, here's P, here's D, here's F. Yeah, that's it. All right, now look.
How would you do one in
Okay, hold on. Look. Now here's what's going to happen. I know, honors class, you guys are all like, oh no, too much information, my head's going to explode. But look, stay with me here. Stay with me because the pattern continues, okay? The pattern continues. And as we go through more and more of these things, that pattern becomes easier and easier to understand because we keep going over it, over and over it. Okay? Huh? That's okay. That's fine. We're going to get to where you're not so wishy-washy. Okay? Yep.
Okay, so like the whole thing with arrows, he was trying to explain to me, but I'm kind of right now. But like, there's like 118.
Exactly.
So like, I don't like, I'm not gonna run 118 arrows. So like,
Yes, you are.
no, I'm not. That's so many
arrows? Will you do? So once you get to
I'll do it.
Listen, here's the funny thing. It seems like so much right now. Okay, I have literally had students that will get near the final exam and will say, "Can we have a lot of those orbital notations? Because I can do that."